We're here to talk about how we're revealing an ocean under siege. And as Florian said, how we're sort of using technology, citizen science, machine learning, and combining that in a really innovative and sort of cutting edge way to try and reveal just how much this ocean is under siege. But first I want to start where it started for me. So I was fortunate enough to go to the South Pacific, find a skipper who needed some crew, and jump on board for 4 months. And I spent 4 months sailing around what you can only describe as a paradise. I mean, it really was the picture postcard ideal of it. But it was a paradise under siege, and we could see that everywhere. And perhaps the most, I don't know if this video is going to work. So you have this off the bow of the boat, dolphins jumping around. So it is pure beautiful, blue azure seas. And the next thing, which you can't help but not see, I mean, this is actually in the UK, but if it loads, will it load? Is quite literally a plastic tide. A tide of litter washing up on the beach, and you can see this from this drone footage. You can see all the litter items just washed up. And this was everywhere. So every tropical remote island you went to, and I'm sure you've all heard it in the news, but this was back in 2008. So when I came back, it really was something that bothered me. I wanted to know how much this is affecting us and the world. And so I started looking into it, and I started finding ways in which I could do something about it. And very quickly I found that it was a massively growing problem. So it costs around the world economy around 8 billion a year at least. You'll see a World Bank estimate that's closer to 12 billion. It's an exponential increase in global plastic production. So by 2050, we're looking at 1.8 billion tons a year. And then I'm sure you probably heard some of these quotes. This is from MacArthur Foundation. By 2050, there could be as much plastic in the ocean as fish. 20% of our oil production will be devoted to plastic production, and something like 15% of the global carbon footprint will be because of plastics. So they're quite harrowing figures, but what sort of impact does that have? This is the actual impact. And apology, I probably should have warned you guys ahead of that, but we've got plastics inside fishes' digestive tracts. So this is out in the Pacific. I think this is albatross, seals entangled, and whales entangled. So that's the reality. But it also impacts us through something called bioaccumulation. And not a lot is known about the toxicity for humans. The biggest concern is that with microplastics, as the plastics break down, they turn into microplastics. Those microplastics act as magnets to attract pollutants, persistent organic pollutants in the water. And there's a lot of interest as to what happens. Do they move from the animals to from the digestive tract into the fish's flesh? And then if we eat that, then do we take on some of that ourselves? And does it accumulate up through the food chains? So there's a lot of concern around that at the moment as well, and there's a lot of research. It's a research priority. Some other key facts, which I'll just throw up there. There's a particular telling one. 8.3 billion metric tons of plastic have been made since forever. 79% of that has gone to landfills and the environment, or the environment. By the way, apologies, my voice is quite squeaky. If I sound like a teenager, I'm sorry. Hopefully it should last. So yeah, those are just some facts and figures up there for you. And so it is a complex problem. There's no silver bullet to it, right? You'll hear lots of things like, we've solved it by having worms that eat plastic. I think the most recent one was an enzyme that dissolves plastic, but that's just the end result. There's still a systemic failure in a way that plastic is leaking and used for example, single-use plastics, as you would have heard. So when I was tackling this problem, I was thinking, well, where does it start? Where do I even start? It's a huge issue with many facets to it. But then one fact struck me the most, and this is actually from a paper by one of our science advisors, Dr. Eric Van Sibbel. 99% of the plastic is missing. Once it enters the ocean, we know about where 1% is, and that's on the surface. It's basically unaccounted for. We don't know the precise mechanisms of where it goes. It's believed that there's major sinks to the ocean floor, coastlines, the upper ocean or the surface, or in the biota, so marine life. So we sort of want to build a 3D picture of how this is set up. And that is important because it helps us resolve the impacts that plastics make. So this is a quote from a paper in 2014. Knowing where it goes, where it ends up, where it concentrates is key for us to understanding what the impacts are. How does it impact human life? How does it impact marine life? How does it impact plankton? And a lot more papers struggle to identify. So the problem is that there's not enough good data to sort of quantify those concentrations in those sinks, and especially in regards to coastlines. So because of our inability to collect data accurately, there are estimates there where we could be underestimating the amount of plastic by an order of magnitude potentially on beaches. So the problem could be far worse than we think it is. And this really struck home to me, having been on the beaches in the South Pacific and having seen it firsthand. This missing element to it really tweaked my curiosity, because at the time I just wondered where it could all come from. I mean, you'd find things like flip-flops and toothbrushes and all sorts of things on beaches, even the bow of a ship which had washed up somewhere. So it was really incredible what you find. So that led me to found the Plastic Tide, where we're trying to identify where those plastics come from, where they accumulate, where do they go, what are the fluxes. So our vision is striving for a plastic-free ocean for humanity. So by understanding where that plastic is, it can lead to our mission. So it's to reveal how our ocean is under siege, and to use that knowledge to better inform cleanup operations, to better inform the damage limitation, impact limitation, and we'll go on to a bit more about that later, and the preventative efforts. And so, who are we? As we can see, so this is our team. We've got a team of trustees. Ellie and Dirk are here with us. Ellie's here with us. Stefan, of course, and Dr. Arturo Castillo is here. But we've also got Dr. Katie Wiles, who's been doing some research with us on the environmental, psychological impacts of beaches, as well as Eric, who's really interested in those ocean circulation aspects. So how are we doing this? How do we detect the plastics? How do we find out where that 99% is missing? Essentially, it's turning what this is. So this is Janie, who was out with me and Ellie on Calgary Beach in the Isle of Mull, manually cataloguing plastics that are collected. Very time-consuming, takes a lot of time. No one wants to do it who's cleaning beaches, because they just want to clean the beach. They don't want to have to sit there for hours figuring how it is. And as a result, Ellie and I found that people in Cornwall would classify what we thought was the same plastic completely differently to someone up in Scotland, even though these people are both professionals and they both know what they're doing. So there's a real problem in getting that clear picture of the concentrations of plastic, which will help us understand the fluxes and the dynamics, which can then inform campaigns and inform in policies and that sort of stuff. Again, we'll talk about more of that in a second. So we set out, so we're basically replacing that with drone surveys. And so we set out to create a vision from the skies, basically, where, as you can see here, Ellie is surveying beaches, Rossili in Wales, for plastics and litter. That gets uploaded to a platform called Zooniverse, which is our citizen science universe, which you can log on to right now, and you tag any plastics that you see in that image. I just uploaded a fresh batch from some US beaches last night, so it's nice and steaming hot for you. And then we apply machine learning, which Stefan will talk about in a bit, and then from that we can identify plastics, and this is the results from our sort of prototype. But eventually we want to sort of cut out the machine learning and the training bit and go straight to the automatic and autonomous identification. And that's the sort of end goal, is to have this algorithm that we can then deploy using drone platforms and scale up that monitoring and detection effort.
So how do you say this platform is called?
This one?
Zooniverse?
Yeah, this is Zooniverse, yeah. I'll send some links. There's some links at the end. And I'll send some to Florian as well. So these are the 33 beaches around the UK that we collected data from. Some of them were our prototype beaches, and others were the main ones. So you can see, so we go to the beach, scan them, and then we did a clean afterwards. Every scan we do, we follow with a clean. That journey led to us finding some of the strange things. So the child wasn't the strange thing to find on the beach, by the way. The little Lego Cutlass, which he found here, and that has a story. So that was a very rare piece of item, which something like 5 million, ironically enough, marine-themed Lego pieces fell into the Atlantic just off the coast of Cornwall 20 years ago, and they're still showing up all over the southwest of England and as far as the Gulf of Mexico and even Melbourne in Australia. So if you do go to the beach holiday, keep a lookout for these, because they are collectible. We gave it to Josh here because Ellie and I wanted him to be our sort of future ocean guardian, and we're happy to say that Josh is extremely enthusiastic about cleaning beaches. So one day he might be coming here and doing a presentation to you guys, hopefully. But we also found a solar-powered mushroom, not quite sure why, and we found a toilet seat, which was great. But we also found the bad and the ugly. So this is a Russian mouthwash from Lever Brothers. A bit of brand naming there, apologies. We found that in Norfolk. Phosphoric acid containers, 4 of them on the beach, just sitting there. And a medical catheter in Scotland. And that's just a sample, and then a syringe on the far right. And it's just a sample of what you'd find. That leads to this. So this is an example of a scanned image. This is cut up, and Stefan will probably talk about in a second. This is cut up into smaller tiles and then uploaded onto Zooniverse, where you can then tag it. This is an example of tagging. So you draw a little box, select which from the drop-down list, press OK, and that's one tag done. And without further ado, I'll hand over to Stefan now, who's our science advisor in electro and robotics computer vision. Thank you.
Thank you very much, Pete. Okay, so I decided to give a bit of a general perspective first on what we are actually doing at Imperial College and how this all feeds into efforts in relation to the plastic tide. So my interest, and that is collaborating with a lot of researchers, especially Professor Andrew Davison at Imperial College, is to work with mobile robots. A lot of things can be classified as mobile robots. We work on the kind of technology behind mobile robots that can be applied to all kinds of scenarios. You know, talking about domestic robotics, we have some funding from Dyson, the vacuum cleaner company, for instance. Drones is a big interest of mine, but obviously also, you know, in autonomous driving, in principle, this is an autonomous robot that needs very much similar technologies for autonomous operation. We're also very interested in advanced manipulation, and things like environment monitoring is one of these applications as well. So if you want to deploy a robot in a fully autonomous way, then kind of traditionally you have to solve a couple of problems. And a typical real-time control loop that would be running on a robot looks a bit like that. You have a kind of perception module here that senses the outer world. And then you interpret all of this data, maybe also some internal sensing, to try and answer questions like, where am I? What does the world around me look like? And with this basis, you can feed that into some kind of higher level intelligence, cognition, planning of actual motion, kind of addressing the questions about what should the robot do and where should the robot go. And then finally, you'll have to come up with actual signals that you send to the motors to make the robot move and to actually achieve what was planned, such that it will then change its state, and the whole thing repeats, right? And so this can be really quite difficult to do because we have to do it in real time. This can potentially run something like 20, 30 times a second. We have to process the data and everything on board. We wouldn't want to rely, for these critical things, you wouldn't want to rely on sending something to a server and waiting for a response, and that might fail. So we have to have efficient algorithms. They have to be also robust. They have to be also accurate enough such that we can achieve a certain task. And I would say the kind of specialty of our labs is somewhat on this side of things, where the whole thing begins, the cycle begins. It's all around simultaneously localizing a robot and understanding, mapping the world. So this is a bit of a chicken and egg problem. And just as a bit of a summary of how we usually tackle that is given here. So there's one piece of research which is all about, it's mostly centered around accurately determining position and orientation of the mobile robot. Okay, so you use several sensors. We definitely rely heavily on computer vision here. But we might combine it with inertial sensing, for instance. We build a kind of a sparse map of just a couple of landmarks in the 3D scene, and at the same time try to find out where the robot, here represented with this kind of coordinate frame, where it is located in a kind of global frame. Of course, you might have GPS, you might have certain aids that help a lot in this problem. But in a general case, for instance, indoor robotics, you wouldn't have that. In the context of the plastic tide, we do leverage GPS. Of course, I would always argue when you have these kind of things available, then you should. So that's kind of the first level. You can already do quite a few things, but when it comes to, for instance, avoiding terrain, not crashing into something, doing safe kind of autonomous navigation in unknown environments, then you need some form of a dense kind of a map. You need a geometric understanding of the world. So this is the kind of next level that we are addressing, and I'll be just showing a little bit of examples here. And then I think that the third level, with enabling somewhat higher level understanding is a semantic one. You don't want to only understand where stuff is, you want to understand what stuff is. And that very much now ties in with the plastic tide. We want to have a mapping system that identifies the semantics behind things. This is an indoor example, but it employs very much similar techniques as what I'll be showing applied to the plastic tide. So we leverage deep learning here that enables us to give us proposals for if something is a bed or if something is the floor. And you can probably see how this could be extremely valuable for all kinds of robotic applications, where now the robot can actually figure out what to do in relation to these objects, where we can have human interaction that relates to these objects that are identified. Okay, so I don't know how technical you all are, but I assume some of you are exposed to machine learning, deep learning. So let me just talk about this a little bit. I think there is a bit of a split in the community between kind of using models, using kind of more engineering-based approaches versus deep learning everything, using data-driven approaches and kind of treat that as an end-to-end black box problem that you want to solve. So I often find myself a little bit in a defensive position for models. So let me start with that. I think models are still very useful even these days. They're very compact. With very few parameters, you can explain an awful lot of things. They generalize also well beyond the training set. So just to give an example here, I would argue discovering physics, the law of physics, kind of very low parametric models have allowed us to do things that are definitely not found in any training data set, before that. And kind of similarly applied to the spatial perception problem, the kind of traditional models, geometric models, probabilistic models, they have really been the success story for a very long time to enable robotics. But on the other hand, use of learning, deep learning, is absolutely is really amazing. And this is it's fairly new that how powerful we see these methods can be. I would argue that it can be used in a very much complementary way, learning relationships that are simply too complex to model. You need to extract it from data. Especially kind of doing things like semantic understanding, that's absolutely the way to go. And we should combine the two things together. And this is very much the same spirit of what we're doing with the plastic tide, is to combine these things together, to combine mapping and semantic understanding together. But just to show what we can do using only the kind of more traditional, but still kind of modern, model-based approach, this is a fully autonomous drone that we have put together. That kind of shows the whole cycle that I've shown in the very beginning, everything operating in here. This is a fully autonomous drone without the need for any GPS or any other external kind of sensing. It has a color and depth camera, including inertial sensing here. And then we have a kind of Intel NUC computer here. It's relatively standard. So this is actually assembled from quite standard components. It's not a very expensive drone. Downward-looking camera as well. So what we're doing here is we're trying to land on a moving platform. And so this is deployed in real. This is completely without any human interaction. It's just a one-button press for the takeoff. And then someone has to run around. It used to be me normally. So it flies to that hovering point, and then it automatically detects and tracks the moving target, and it will land on it safely. And the tricky bit is it doesn't have to just work once. It has to work under different environmental conditions, even on a nice sunny day, wind and so on. So you don't just do it once for a paper, you submit it and you're done. This has to work really robustly. I guess that's the main challenge here. But it can be done. So there's absolutely no learning involved. But at the same time, I guess we have to understand the limits. So let me just bring up this slide. I won't go into too much technical details, but effectively, the kind of traditional approach to simultaneous localization and mapping, SLAM, consists of very much kind of this building these models. So what we do is we model out the measurements as samples from a probability distribution, and then we are trying to find the values that best explain all the measurements. This is instantiations of a maximum likelihood or maximum a posteriori problem, usually. And we have to take a couple of kind of engineering decisions. We have to decide how we want to represent the robot, where it is positioned, what orientation and so on, as well as how we represent the environment, the map. Then we have to model these distributions. And then here's the most engineering, really. We have to choose a lot of approximations, ways of how to solve this optimization problem, for instance, or a filtering problem. We have to find also some way to initialize, to bootstrap, to get started. And so that's a traditional way of doing it. And now we can bring in learning. We can bring in learning, for instance, to have this semantic map layer that I mentioned before. We also can find representations that are sort of aware of the semantics behind it. It's very wasteful to try and represent a map with just millions and billions of points, for instance. So we can try and find more compact representations. We can also learn geometry. So this is another very interesting field at the moment where deep learning can be leveraged to actually understand kind of geometric priors from just looking at an image. Okay. So just to give you an example, so this is how we would, for instance, represent the state of a drone. So this could be a drone as it is being flown autonomously to inspect the beach. At the moment in the plastic tide, we were still using manually controlled drones, I should say. But this is now our fully autonomous drone that we have at the lab. So we'd usually have a kind of a combination of, this is position and orientation of the drone, a combination of kind of physical states that we need to control it, also the velocity here. But then things like online calibration to calibrate the cameras with respect to each other, even in the real-time operation, as well as some sensor intrinsic kind of biases that we need to estimate. So you can see this kind of just shows a little bit this kind of first choice that we have to make in terms of how to represent the state. And then here's the second choice, and I think this is also super critical, and it really depends on the application you want to target. On how to represent the environment. Traditionally, things like point clouds were used. We also see fully, sorry about that. We see fully volumetric approaches. We see meshes. They all have their advantages and disadvantages, so I'll show a couple of examples about that. And so in the most traditional kind of way, we might just represent the world as a couple of sparse 3D points. So when you now try to do the mapping process, or the simultaneous localization and mapping process, you have to first identify corresponding points from one image to the next, or just between images. So this is an example of how this is being done. You have to detect points, and then you have to find a way to match them with some kind of local descriptors. So this is the vision side. So the vision side of things gives you some kind of spatial information, right? Gives you ultimately information about how the camera has moved as a relative pose, how the camera has changed. And now we can also combine that with complementary sensing, like inertial ones. And this really is the backbone of any kind of drone, autonomous drone operation these days, is to combine these two. So here's just some work that does that. You can see here how the camera is, how images are matched, how key points are matched with respect to live image here with respect to a keyframe in the past. And on the right-hand side, you can see how now this estimator estimates where these 3D points, sparse 3D points are in the world, as well as where the drone is located as it's flying around, including the orientation. And again, this has to run in real time, on relatively constrained platforms. We're still talking about the kind of i7 here, so it's not as bad as it could be. And then it has to be accurate. It has to be robust, also when you have aggressive motion blur potentially. And low lighting conditions, difficult lighting conditions here. Okay, and then at some point the drone is coming back, and you will see that it's pretty much coming back to the same position in the end. I'll skip the rest here, but this is the kind of missions that we can do now. If we sort of know where it is safe to fly, we can completely autonomously create the mission. We can send the drone to waypoints and do something completely autonomously. Okay. So that was the kind of first layer of simultaneous localization and mapping. Clearly, we would like to go beyond that. We would like to enable avoidance of collision. We would like to deploy these robots in environments that are not as trivial. And so we've also created some dense mapping approaches, where now this is actually using depth cameras. So we have as an input, you'll see that in a second here, the RGB image, the live feed, as well as the depth images from the camera. And the camera is being moved around, and we kind of stitch together these little snapshots of a map by simultaneously finding out in a kind of alternate fashion here. First you try to find out how the camera has moved, and then you put the new information into a very dense map. And we can actually also correct drift. This is something that will always happen. Once you move it around in a loop or so, you come back to a place that you've seen before, you will have some accumulated drift. You will start to remap the same instance again, and here we can detect that, and we can make corrections. We can actually deform the map and have a consistent map over a long time that we put together. Okay. So this is kind of technologies that you can use now to have a second level that enables collision avoidance and path planning. But let's now get to semantics, because this is also what we're leveraging in the plastic tide. So once you have a method that lets you create a map and potentially simultaneously tracking the motion of a camera, now we can augment the map using some kind of semantics. So here we are using exactly this kind of process I've just shown on the slide before. Okay, and then, so here it runs in parallel. And then we run deep learning enabled semantic segmentation on top of that. So the principle will just show in a second. So we use the live feed from the camera, RGB image plus depth image. We do a reconstruction, a dense map. And now we use in parallel the same inputs, feed them through a convolutional neural network. And the convolutional neural network was previously trained with lots of data. That's the key here. We need lots of data to train it, such that it can then make these predictions. It can interpret the data and it can find out, okay, well, this is floor, this is sofa, and it will give us these maps as probability maps, essentially, or we can interpret the output after the training as probability maps. And we can fuse this information, we can accumulate this information into the 3D world, so we get a semantic map in the end. So in some sense, this is already kind of how I see how the plastic tide version 2.0 could work, where we have a very accurate, very dense 3D representation of the world, and we have annotations about what these things are. So here, this is an indoor environment. It was trained with things like floor and windows and chairs. But you could imagine that these could be, with the right training data sets, these could be different kinds of plastic pieces that we can very accurately now localize and map in the 3D world. I'll somewhat skip the data here. The interesting bit is that actually accumulating this semantic information in the 3D world helps you getting more accurate in your semantic segmentation when you just project it to the 2D image. So it was an interesting finding. Okay, so now linking that to the plastic tide, it's a very much similar process, right? So we accumulate. We have to get very specific data. That's the trick about machine learning. We need to find the environment in which we want to deploy the system. Ultimately, we need to create training data there, and so this is, thanks to Pete and Ellie here that went around and collected a lot of drone footage. Again, this is manually controlled, but it really doesn't matter. It's just a matter of creating a lot of. I switched this off somehow. It doesn't seem to care. Sorry. So you have to create a lot of imagery, and then it has to be tagged. We have Pete has all the statistics about how many tags we have. We had to split up the original high-resolution drone images into tiles. Then they are presented to the taggers. We get a lot of kind of ground truth annotations, and we train our network. In our case, it is the YOLO version 2 simultaneous bounding box detection and classification algorithm that we use. So I'm not a deep learning expert. We didn't kind of try and change the architecture of this network. But the way you can think about it, for those who are not experts in machine learning, is that you have this network that effectively consists of a lot of parameters, probably millions of parameters that are then being learned. That it fits the data, right? That when you input the data here, that would be an image, such that you actually get the kind of outputs that you give in training. So you're giving it a lot of examples like this, and ultimately it will be able to autonomously detect these kind of plastic pieces. So here, this is a level of just bounding boxes that we get out. The example before showed segmentation. So that's where we want to ultimately get to as well. But I think this is a very important starting point to just have bounding boxes and kind of rough idea of where these pieces of plastics are actually located. So here's a couple of examples of how that actually then works in practice. This is very much ongoing work. We're trying to improve that at the moment. So this is just at the level of one image in. What kind of plastics can we detect in the image? You can see here. That's now, just to emphasize that one more time, this is now not training data. This is what the network has learned. So this is completely automatic. You give it an image, it will tell you where are the plastic pieces. And it finds some really quite surprisingly small things as well. But it also makes mistakes, right? So here, for instance, you see it how it's kind of double detected the same thing. Here as well. I think here it's missed something, although I can barely see that on the screen. So it does miss certain things that are also actually difficult to see for people. So I'm confident that with enough data, we can train an algorithm that will be at least as good as people are. So that should be really the goal, right? That we can automate this process of then ultimately mapping these pieces, right? So that this is the idea that we can now put the kind of mapping infrastructure that I've shown before. We can put that together, assuming we have now the very precise localizations for where these images were taken. We can triangulate them into the real world. Combine that with GPS knowledge, and we will have a very accurate map of where there are plastic pieces. At the moment, still just kind of bounding boxes, kind of in 3D in the end, but the goal is to go beyond that. I'll skip this for a second, and I will just mention this as well. So just talking about training data, in the case of the plastic tide, we made a lot of effort to actually get this training data, real training data out there. Indoors in the lab, we work with also synthetic training data, so this is a sort of way around it. For these machine learning algorithms, you need a lot of training data. You need hundreds of thousands and millions maybe of images, but we can get away to some degree at least with simulating actually. So we have built some simulators simulating indoor environments that give us perfect ground truth. But of course, there's always a question about how realistic these images are. It's a bit of a messy room here, actually. We would hope to not necessarily see that really, but we want to train the algorithms to be able to deal with any kind of situation. Okay, so this is kind of open training data sets that we have. We're also moving somewhat beyond that. With very realistic, trying to get more realistic training data sets with having very professionally designed, interior design kind of elements, and then we can render scenes like that. But you can imagine that replicating this process is probably quite difficult for a specific setting like outdoors and beaches, where there's just very little understanding also about what's going on. So here we can leverage, designs that people have made in the past. And maybe a bit also more interestingly in a robotic context, if you want to have a ground robot, what we can do now is we can render the scene from a quite unusual perspective. And I think this is again kind of in the same spirit as I mentioned before. You have to make this specific for the application, right? You have to have the right training data for the right application. So if you have a ground robot, you probably want some kind of ground robot type footage. If you want a drone that finds plastic pieces, you need training data from plastic pieces on the beach. Okay, so I think I'll close on that note and I'll hand over back to Pete to explain a little bit the next steps, I believe, of the plastic tide. Thank you.
Thanks, Stefan. So that's a really fascinating look, in-depth look at the sort of what's happening behind the scenes. So when we're talking about machine learning and how we apply it, that's the sort of output and the type of things we're aiming for that algorithm 2.0. So for our sort of production algorithm that we want to get to, which we're working on now, is sort of being able to localize, identify, where the plastic item is in its location, what size it is, what kind it is eventually. Also the sort of volume using the SLAM techniques that Stefan was talking about, as well as having an autonomous platform to scale So you're not just, we'll talk about it in a second, scalar, but as long as that's within the sort of legal and safe framework. So I think there's a bit of human interaction at the start to ensure that those platforms operate within safe environments, especially given congested airspace like is around southeast England. So some of the application, what does it all mean? So great, we've got the scanning, we've got the data, but how will this have an impact to what I saw at the very beginning and my journey to that broader understanding of the problem of where plastics are, and then eventually how we can help prevent, how all this technology that reveals the extent of the problem can help prevent the problem in the first place, as well as help clean it up. And so the first thing is the localization and trend analysis. So this data is actually data that we manually collected, but eventually through the algorithm outputs, we'll be able to sort of heat map, hotspot analyze concentrations of plastics, and then sort of pull from that data about the types of plastics. All sorts of analysis, again, depending on the requirement. And this data is the thing that's missing at the moment, at this sort of scale, because it only happens in very localized ways. It's very hard for the person to get the exact same volunteers to go to the exact same beach that they were before and record it in the exact same way. Whereas the algorithm, although it's not going to be perfect, we don't think we can get it up to 100% at all, but at least if there are errors, they're more consistent, which allows scientists to understand that background. And that sort of thing can inform things like legal monitoring enforcement. So there's all sorts of conventions now from the UNCLOS, the United Nations Law of the Sea, which is all about monitoring impact. So if there's leakage into the sea, member states have an obligation to then monitor how that is impacting the environment. That has then been transposed to EU regulation through the European Environmental Strategic Marine Framework Directive. And they've got a policy cycle here again where they need to monitor. So GES is good environmental standard. There's lots of things involved in that, but one of them is, again, marine litter on beaches. So when you go to a beach and you see lots of marine litter, legally now that shouldn't be there, or states should be monitoring that and putting plans in to prevent it. So this is part of the strategy, and that all comes under the Honolulu strategy, which was a big effort to get not just policy people and governments, but also companies involved in that design and the appreciation of how do plastics break down, what are the most ones, how can we identify which are the most offending ones. And this is a lot of sort of Dr. Arturo's work here, Dr. Castillo's work, to quantify risk to wildlife. So as you saw some of these pictures, this is someone sent in the seagull. He caught a seagull eating a bit of plastic on the beach right in front of him as he was doing a drone scan. So if we understand the sizes of plastics and where they concentrate, and there are some NERC calls, some research calls now about this, and using the localization and SLAM, the semantic segmentation, we can understand the sizes and types, and that will allow us to sort of map that with, say, feeding patterns of albatross. So we can then identify those marine environments that are most vulnerable to plastic contamination. But also to quantify the risk to humans. So this is in Tonga, this is Nuku'alofa, this is near, so it's not far from where I was in the South Pacific. And it helps us understand the risks to humans. So whilst we don't yet understand the transfer of toxins, and that's subject for intense study at the moment, the UN is advising a precautionary principle. So rather than waiting for the stuff to hit the fan, we do something about it now. And so it's really important understanding with something like, I think half the world's population lives within 100 kilometers of the coast. So there's an important interaction going on here. It allows us to quantify that. Economic damage to shipping. Here's a ship's propeller tangled with a netting, and that ship is then disabled. That ship is then vulnerable. If it was in a storm, it would be vulnerable to capsize in that. To the tourist industry. I've got friends who've gone to Phuket, and they now see plastic all over the place. And that impacts, no one wants to go to a beach and sit in basically a rubbish heap, So a lot of there's a lot of interest in there, as well as below is the sort of economic environment affecting harbours and ships, and so there's lots of potential applications in that area, and then that can lead to obviously coordinating the removal. So this is the group of us here. This is the final beach clean in Dovercourt in Essex, and help more effective from local organisations, volunteer groups, all the way up to sort of governmental level to help pinpoint the best area, the most effective areas to clean. Because if we know how much of the litter is coming in from the sea, how much of it is coming from the land, where it accumulates, it will help us tackle that aspect. It could help us identify what types of plastic, which then leads on to the next sort of element, which is informing campaigns and effectiveness. So if you say, all right, well, we're going to ban all drink bottles, or we're going to instigate a deposit return scheme, well, how do you measure how successful that is? Without that data, it's difficult to lobby. There's one less as well. There's Sky News Pass on single-use plastic, Pass on plastics. There's some great campaigns out there. But we need to understand what sort of impact they're having on the environment to ensure that they're the best they can be to really help get to that end goal of a cleaner ocean. Some of the impacts, and not long now, it's nearly finished. We've done over 33 beaches with over 100 volunteers, a ton of litter, 14,000 drone images. I think we've probably got, because each drone image is divided into about 25 tiles because of the resolution. And each tile is then uploaded to Zooniverse. So I think we're more in the region of 500,000 images that we've gone through. We've had over 10,000 volunteers. We're nearly at 4 million tags now. Last week for British Science Week, a couple of weeks ago, we got 1.5 million in 5 days, which was incredible. Tens to hundreds of schools, so we know lots of schools got in. The demand peaked during school hours from 10 to 3 p.m. We were getting something like 1,000 tags a minute or something like that. It was incredible. It's national and eventually international. And then tomorrow, so this is the phase 2. So this is sort of 2.0, which we were talking about. The production algorithm, a global database, all of that imagery, that data gets uploaded to a map online, where you can then view, visualize, and query the data. Eventually autonomous drone platforms, open source, so we want to release as much as we can open source licenses, extending it to the sea floor, sea surface, and rivers. So you remember that diagram at the beginning where we looked at all the fluxes. So retraining the data set, and we're working on prototypes now for the sea floor, for example, so keep an eye out for that. Moving to multispectral and hyperspectral imagery. Then satellite sensing, potentially even gamifying the citizen science element. So it's a very dry interaction at the moment. It's only great on computers. It's not great on mobiles because it's a volunteer platform and they do it free of charge. That's Zooniverse. It's part of Oxford and sort of drone survey standards, setting up an international standard for drone surveying, which we've set up a Marina to drone net to support that. And we've got people from around the world on that, which we're launching on Sunday. Which is World Earth Day. And then just a little about the timelines, rough approximation of the sort of timelines in which we're looking at that. On how to get involved, I'll send some links around to Florian. Numero uno is get tagging. Also, I think we're now registered with Google Giving, I think it is. Yeah, so if you want to give some of your time or some of your efforts, you can tag. We'll be setting up beach cleans as well, so go to our website, www.theplastictide.com, and you'll see all the latest things that we're doing. I've got a talk next Tuesday at a conference. I think that's it. So any questions, and thank everyone. Thank you.
So did you say a couple of slides back that we can actually go down and take our own drone images, which we can then get people to tag? Yeah.
Potentially, yes. We do that. Ellie and I set up a sort of standard where you can donate, and we have a structure where you basically He gives the images, and then we upload them. So, but eventually, once we've got enough of that training data, we'll be moving away from that. But there are areas where we could explore it for further citizen science. So we know that when people have had to look closely on the tagging side, you then start to see a lot more of it outside. And that starts to change your behavior. And so like I said, we've got a researcher who's looking into that now. So.
Cool. And for the image quality, do they need to be of a specific image quality, the drone images?
I was wondering how flexible your platform would be for other forms of environmental aerial survey. So I know that, for instance, people are looking at the spread of sudden, tree diseases, say, from canopy surveys, and I wondered whether it seems like a lot of the platform you would already have built for this, and maybe it's just the final bit of like visual machine learning that would be required to be changed to do things like handling multispectral images and looking at tree health.
Yeah, I guess it's somewhat a question for both of us, right? But I mean, from the machine learning perspective and robotics perspective, you're absolutely right. It doesn't really change the principles behind it. But at the same time, you'll still need the training data that is specific to that application. And I think that's when the plastic tide kind of setup would need to come in for a different application. But yeah, in principle, we would be ready, right? Also, Zooniverse or other platforms that enable tagging, they're out there, and
there were canopy tagging platforms on that, and we're sort of talking about, when we're doing the seafloor monitoring and potentially on the beaches as well, as perhaps looking at marine life and keystone species. But again, it's very difficult because you've got to think about the tagger on the other side and their level of expertise. So it's quite a balancing act. You don't want to overload them, otherwise you're just not going to get the volume you need. So.
Thank you for an interesting presentation. I wonder if the technology enables us today to scan the ocean or like the seas and to get the exact picture, because you mentioned the 99% it goes sinks to the oceans or the water, right? And the 1% it's kind of rough calculation maybe, but if the technology enables us today, and another is like how we influence once we get all the data, how we influence because you mentioned the policy, how we influence policymakers or the consumers in the future to kind of restrain from the plastic use or to ban the plastic for the future. Because I know there are a couple of, I think that France introduced the policy with the ban the plastics, and some of the countries are like in the queue as well. Thank you.
Just today, actually, I think there was news that for the UK, plastic straws will be banned.
You just announced it 10 minutes ago.
Oh.
Yeah.
Okay.
Plastic straws banned.
Yeah.
There we go. Boom.
They're banned. So I definitely, I think politics are waking up. There still needs a lot more waking up and then actual action to follow. Yeah, I hope we can feed some of that data. But that's probably more of your.
Yeah, I think we've got an
expertise.
expert in the house right here. So I think if we can pass the microphone to Arturo. So Dr. Arturo is at Imperial. He can introduce himself.
So we know what the policy making cycle is, and it all starts with also sentiment monitoring of people. So politicians and policymakers don't move unless they know that there is a demand and a need for all these policies to actually take place. And the way the plastic tide can do that is by informing what are the trends, what is the frequency and the hotspots of all this damage that is accumulating, and raising the awareness. So this is very important that this has two elements. One is the monitoring, but the other one is the education. And the moment that people are educated, then both the demand and the welcoming of the policies will be much easier.
We are running out of time, so we have to close here again. Thank you very much.
Thank you.